Hello everybody and welcome to this tutorial video on how to use the basic functionality of the Causion application. Causion is an app that lets you visualize the expected consequences of changing variable values in a directed acyclic graph, or a DAG. So the purpose of the app is to let you manipulate variables and see what happens to other variables given the causal effects that exist between those variables. And the app also lets you visualize what data from directed acyclic graph looks like. So you can combine the knowledge of the DAG with knowledge about what data patterns you would expect to see if you collect data from a particular directed acyclic graph. All right, so without further ado, let's get started. When you open the Causion app, the main display shows you this simple DAG. X causes Y is represented by this DAG. So the circles here are called nodes. They represent variables whose values we can change if we like. And the edges here represent, or arrows, represent causal effects. So each arrow points from something that causes X in this case to something that is being caused Y in this case. And that's the main panel that we interact with. There are also some more advanced functions and an ability to visualize data. So that all lives on the top right section of the application here. I'll explain how each of these buttons work in just a bit, but let me first show you how we manipulate things in the DAG window itself, actually how we build and edit and manipulate the causal hypothesis that we want to explore. When you click on a node in the DAG, you will see that this mini menu pops out underneath the node. And the mini menu contains 3 buttons and a slider. And this is the basic way that we can manipulate the values of a certain variable in the DAG. So suppose I want to change the values of the X variable and see what consequences this has for the Y variable. The easiest way to do this is for me to just drag the slider value here, which you can see both changes the color of the variables. Blue color signal positive values and red color signal negative values. And you see that the numbers on the variable changes as well, and this represents the exact numerical change in the value. Notice also that when I change the X variable, I'm changing the Y variable because X is causing Y. For now, the change is exact. So if I change X to 36, Y also changes to 36 because Y is essentially just equal to X in this DAG. And I'll show you how we can manipulate the exact size and functional form of the causal effect later. But this represents the basic way that we can change variable values. If I drop the slider value, it resets to 0. We can change that by applying the do function, which I'll talk more about later on. But there are also 2 other ways to change variable values. If you click the play button over here, then the slider will slide automatically from the bottom to the top of the scale back and forth by itself. So you can basically start a variable and leave it. I can even deselect the variable, click another variable, and the X variable will keep changing its value systematically up and down on the scale. The other way to automatically change values is the die button, which just randomly changes the values of X. So it just uniformly draws a random value from minus 100 to plus 100. And that also happens automatically. So if I deselect this, X keeps changing its values constantly and exerts its causal effect even if I'm not pressing anything. Now, suppose I want to make changes to the causal hypothesis that I am exploring. For example, perhaps I want to study a specific example. Let's say I want to look at whether smoking causes cancer, and I may also want to take a look at some other potential causal effects that I think influences this relationship. In order to implement this example, I should first change the variable names of the nodes. And that's quite easy. If you select the node and press the variable name, you can rename it by just writing a new name. So for example, I can call this variable smoke, and I can call this variable cancer. And if you hit enter, you save the new variable name. Perhaps I would also like to reposition the nodes slightly. If I want to do that, if you click and hold a node, you can drag it around on the screen, so you can change the positions. The edges will naturally follow the nodes as you move them around. And you can also move multiple nodes at once. If you hold down and click Control while pressing multiple nodes, you select all of them and you can drag them around as a unit. Alternatively, if you press Shift and drag this selection bar over multiple nodes, you select all of them, and again, you can move them around. To deselect, you just press an empty part of the window. In order to create a new node, we simply double-click somewhere in the empty section of the panel, and you'll see that a little dialog box appears that asks us to create a new variable name. Suppose I think that there is a genetic effect that might be involved in this causal relationship. I can simply write genes as the variable name, and if I hit enter, the variable appears in the DAG. Again, I can drag this around, and you'll see that if I select a variable, there are these 4 light gray arrows pointing out of it. These lets us connect new edges between nodes in the graph. So if I want to make a new, let's say, for example, I think that genes is a confounder that influences both people's tendency to smoke and their tendencies to develop cancer. I can connect this variable to the 2 others by clicking and holding one of these light gray arrowheads and dragging a line over the variable I want to connect it to. So we select what we want to be the cause, and we drag the effect to what we want to be the effect, and then we release, and a new arrow is created. And I can also do this for cancer. And now if I change the values of genes by clicking it, you'll see that it exerts a causal effect in line with it being a confounder. Now, we may want to change the actual nature of the causal effects here. So maybe we want a certain causal effect to be negative, or perhaps we want to change the strength of a certain causal effect. We can do that by clicking on a node, and you'll see that this number 1 appears. Actually, every node has a number 1, and that's just a way to make the causal effect an identity property. So if genes equals 1, then smoke equals 1, because smoke equals 1 times genes, basically. But we could perhaps want a smaller causal effect, so I could write 0.5 here instead. And if I do that and change genes, you'll see that smoking is no longer equal to genes. It's equal to half the value of genes, and that's because we have halved the causal effect. If we can also write negative numbers here, so perhaps it's easier to show if I change this value around. If I write -1 here, press enter, and then change the value of smoke, you'll see that now as smoke increases, cancer decreases, whatever we mean by the values of cancer. And that's because we have now set cancer to be minus the level of smoke. The causal effect formulas are not displayed by default for simplicity or to avoid visual collider, but we can easily show them by clicking this button, Show Edge Formulas, up here. If you click that, you will see the edge formulas for all the edges in the DAG, which gives you easy access or easy overview over all the causal effects in the DAG. Both nodes and edges can also be deleted from the DAG. So suppose we want to remove the effects of genes on smoking tendency. If you select an edge and simply delete it, the edge will go away. And we can also delete an entire node by selecting it and pressing delete. And pressing delete on a node also deletes any incoming and outgoing edges from that node. One of the main functions of the Causion app is to help us explore the relationship between causation and correlation. So the app is designed to help us make changes in a DAG and then see visually what kinds of correlations are produced by different changes to the DAG. There are two main ways to explore this. We can simply make changes to a variable and look in the DAG at what happens to other variables. So if I press play on the smoke variable, we can see that it causes the cancer variable, and we can just look at the color changes and get an intuition for the correlation between these variables. It seems that whenever the smoke variable goes up, the cancer variable goes down, and vice versa. Their color changes are inverse. If I were to, and that's because the causal effect is negative right now, but if I make the causal effect positive, you see that they change colors in tandem. So positive changes in this variable leads to positive changes in this variable, and vice versa. And this synchronized color change tells us that the two variables are correlated. But there is a different way that we can study correlation between the variables. We can also open the Visualize Data panel of the application. Let me just make that a little bit bigger. The main feature of the data panel is this scatter plot over here. The scatter plot samples values from the DAG when we start to change values in some of the variables, and shows the correlation, what the correlation in data would look like between two variables if we were to change one or the other. We can select which variables to look at. So you can see that cancer is now displayed on the x-axis and smoke on the y-axis. And we can change that in the variables subpanel over here. So here all the variables in the DAG will be listed, and we can select which one we want on each axis. This is maybe easier to see if I also add back this gene variable and connect it to smoking and cancer as I did before. Now you can see that the gene variable appears here, and we can choose whether we want to look at the relationship between the gene variable and the cancer variable, or between the smoke variable and the cancer variable. In order to generate some data for this plot, we simply have to start manipulating some of the values in the plot. So if I would like to see what happens to the correlation between smoking and cancer if I change the values of the smoking variable, I can press play, and you see that this automatically starts to simulate data points. Now, you don't see any more being simulated now because they completely overlap, but I can also randomly select values, and that'll help show you that new data are being sampled all the time. And now, what we can see from this plot is that smoking and cancer is completely positively correlated. Like, the correlation is 1, and that's because there is no noise in these measurements. So it's just cancer is purely a function of smoking right now. Also because we are not changing the gene variable at all. But of course, this is not how the real world works mostly. So if we want to, we can also add some noise to these measurements, and that's done through this noise panel at the top right of the application window. Let me show you how we, so first of all, if I want to sample new data points with noise, I might want to clear the data points I've already sampled, and I can do that with the clear samples button over here. The one data point that remains here is simply the one data point that's sampled from smoking being 0 and cancer being 0, so that'll always stay there. And then no new data points are sampled until we make changes to the DAG. I can now press the on button on the noise panel, and you'll see that this activates a slider that lets me control how much noise I want to have in my measurements. And you'll also see that in the DAG panel, when I have turned noise on, these little hidden nodes appear. Now, these represent what noise actually is in the real world, which is just unmeasured variables that we can't control and can't measure the value of, but that nonetheless influence the variables that we're interested in. So we can't actually select or move these variables around. We can turn noise off to make them go away again, but they're hidden to represent the fact that these are variables that cause us changes to stuff we care about, but that we can't observe directly. And now if I change the value of smoke, the application will also make sure that these variables influence the variables we're interested in, and that'll change what the output values end up being for the variables that we do observe. So if I press play now and look at the plot, you'll see that there is still correlation between smoking and cancer, but there's clearly some noise in the measurements now. That's resulting from the fact that these unmeasured variables also change values that influence the cancer variable. If I turn noise level way up and clear to sample again, you can see that this now creates a very wide variety in where node values are presented in the plot, because there is now a lot of noise in this measurement. If I turn noise way down again, you'll see that there's almost no variation around what seems to be the central line. If you want to see what the central tendency is, we can also add a regression line to the plot. Either a linear one, like here. It's almost invisible because there is so little noise now, but if I turn noise level up again, this function becomes more useful to inspect what the actual correlation is. And we can also add a nonlinear regression line, which isn't so useful now that we're only operating with linear causal effects. But you can specify nonlinear causal effects, and then this type of regression line becomes more useful. It's also possible to simulate data from the DAG and download the simulated data to a CSV file. This is quite easy. We just go to the simulate panel down here. We select a number of simulations that we want, so the number of rows in the dataset, and the simulation will automatically simulate data points for all the variables we're interested in. We also need to decide if we want to simulate with or without noise. If we simulate data with noise, like now when the noise function is turned on, then the simulation will basically update the values of these unmeasured variables and add that to the output simulation before saving the data, so we get noise in the measurements. If we turn noise off, what the simulation will do is find all the variables in the DAG that doesn't have any parents, like gene over here. Gene doesn't have any parents, and it will randomly simulate the values of gene, then compute what the resulting values would be for smoke and for cancer, and then it will store those values. So that'll give you a simulated data, but where the causal relationships are perfect in a sense, or unaffected by noise. If you want to then export these data, you just click Export CSV, and that automatically opens a dialog box to save the CSV file somewhere. Finally, if we want to remove the data panel, we can either just click the Close button over at the top right, or click Hide Data over at the top right panel of the window. And this takes the panel away, so we can basically choose whether to display or not display this. If you open these panels, by the way, you may sometimes want to realign the DAG, like sometimes the DAG might turn up in an edge like this. And to realign, we can just click the Fit View button on the bottom left, and that recenters the DAG so that it's easy to see when you have one or multiple panels open. Another important function that we can play around with in the DAG is the do operator that I mentioned before. The do operator basically lets us explore the consequences of doing an experiment on one of the variables in the DAG. A randomized experiment, to be specific. If we want to activate the do operator, we just press one of the variables we want activated for, and then we click the do button down in the mini menu over here. And you'll see that this automatically turns all the edges that point towards the variable that we just activated the operator for off. in the sense that the edge becomes transparent and light gray. This is because we are essentially saying that we are now controlling the variable smoke, and no other variable is allowed to control it anymore. So this is how a randomized control experiment would work in the real world. And if we now change the values of smoke, the slider doesn't reset if we drop the slider, and that's because we're saying that we control this level. So we can basically set smoke to a specified value and see what happens to the DAG if we force smoke to take a certain value. It also means that if I change a different variable over here, so if I were to change the variable gene, you'll see that it no longer influences the value of smoke, which is consistent with the fact that we are now sort of doing an experiment where it doesn't matter what genetic material you come into the experiment with, we are going to decide how much you are smoking in this particular situation. If you want to turn the do operator off again, you simply click the button again. You'll see that the incoming edges reappear to signal that now the variable can be affected by other variables in the DAG. Also notice, by the way, that in the data panel over here, the data panel doesn't automatically detect that we've made changes to the DAG, so it looks kind of crazy right now because we've tried to change variable values after doing different changes to the DAG. So normally, if you want to study the effect of doing some change in the DAG, you should clear the samples over in the data panel and regenerate the data. Finally, the Causion model has a button called Advanced Functions. If we click the Advanced Functions button, we see that this panel column appears on the left side of the screen, and it contains two sub-panels. The first one is called Assign Values. An Assign Values panel is essentially just the collection of all the node mini-menus in one list. So you'll see here that there is a section called Cancer, and that has a slider and a play and a randomize and a do button. And that does exactly the same thing as the mini menu over here. So if I change the slider value over here in the Assign Values panel, it changes the value in the mini menu slider. That's because those are identical. And if I were to click the play button, for example, that does the exact same thing as clicking the play button on the mini menu. The Assign Values panel can be easier to work with if you have very many variables rather than clicking around on all the different nodes. And it also gives you a better overview of all the changes you've done to nodes in the DAG. So for example, if I want to do some more like advanced configuration of the DAG, let's say I want to do activate the do operator for the gene variable and also for the smoke variable, and then I want to randomize the cancer variable. You'll see that this can quite easily be done through the Assign Values panel. It's also possible to pause a simulation in the Assign Values panel. So if I click pause now, I freeze the DAG in the middle of a simulation. If I want to look at a particular state, I can resume by clicking resume. And if I want to reset all the changes that I've made, take away all the buttons I've activated, for example, then I can just press reset over here. And this resets all the stuff I've done to all the different variables over in the DAG. The Assign Values panel also contains one more feature, which is listed over here, and that lets us both determine the exact value and the scale of each variable. So suppose I want to set a particular value for the cancer variable. I first need to activate the do operator so that I can set it to a specific value. And rather than trying to hit an exact value with the slider scale, I could simply write a value in here, and it will automatically update to the value that I set. More importantly, I can also change the actual scale of a variable in this section. So if I would want the cancer variable to take a different range of values, Let's say that it should change from -1000 to +1000. Now, if I drag the slider of the cancer variable, you'll see that it changes from -1000 to +1000 instead. The second panel in the Advanced Functions panel column is called Structural Causal Model. And this is where the structural causal model for the DAG that we've created lives. And you'll see that over in the dialog box here. This basically represents the algebraic equations that correspond to the DAG that we've drawn. So the way you read a structural causal model, the caused variables appear on the left. So for example, here is cancer, and the structural causal model says that this is a function of smoke plus gene. This would be the same as saying that it's a function of 1 times smoke plus 1 times gene. And that is exactly the same as the DAG tells us. So in the DAG, we can see that cancer is a function. Well, I should turn the do operator off. Cancer is a function of gene because gene causes cancer, and also of smoke because smoke causes cancer. And both the effects are 1, corresponding to the 1 times over here. But because 1 times smoke just equals smoke, we can usually leave this out of the equations. As you can see, the structural equation model is editable, and this is a different way that we can actually edit the DAG. Let's suppose I want to give the gene variable a parent. So I want to create a variable that is called parent and make it a causal parent of gene. If I write this into the structural equation model and click apply changes, you'll see that the model regenerates. So I have to move things around again. But importantly, now there is a variable created that is called parent, and it's causing the gene. And it's causing the causal effect is exactly 1 because I've said that smoke equals gene. If I want to change the causal effect sizes over here, I can also do it in the structural equation model. So for example, if I want gene to be 1/2 the value of its parent, I can say gene equals 0.5 times parent, click apply changes. And now you see that the edge formula has changed over in the DAG. So if you want to make many changes at once to the DAG, this can be an easy way to do it that gives you a good overview of what has changed. Another practical aspect of having the structural equation model available is that you can copy this text and paste it into a text file. And that essentially saves your DAG. So if I were to copy and remove this from the DAG and then click apply changes, now there is no structural equation model, so the whole DAG disappears. But if I then paste the same text into the structural equation model dialog box and click apply changes, the DAG reappears because the structural equation model contains all the important structural information to recreate the DAG. So if you have a particular DAG that you're working with and you want to save it and work on it some more later, you can just save it in the text file on your computer and then copy it into the app again. There are also a few buttons in this panel to load pre-generated DAGs. So for example, if you want to load a simple confounding model, you can click load confounding. You see that changes the structural equation model. And if you click apply changes, this loads a simple confounding model where C is a confounder that influences both X and Y. And we can load a mediation model as well, a collider model, or a slightly more complex model with many different causal relationships. If you want to learn more about how to create structural equation models yourself, you can see how to do that by opening the cheat sheet for the structural causal model panel by clicking this little link, which opens window in window. That contains a cheat sheet that explains how you set up these structural equation models and what types of functions you can add as causal effects. So that is all the basic functionality contained in the Causion app. It is a simple but quite powerful application for simulating causal effects. If you want to check out the code that is underneath the application, you can check that out at the GitHub repository for the app, which you can find by clicking on this little GitHub icon next to the DAG heading. If you have any suggestion for improvements of the app, or you spot any bugs that needs to be fixed, please submit a GitHub comment or just leave a comment in the YouTube video below, and have fun exploring the wonders of the world of causal inference.